Okay, last lesson of Unit 6 circles. And this is a bit of a review and some applications, kind of mishmashing everything together. So this video will be just some guides for you to kind of get things completed. We might walk through the warm-up together, and then I'll say a couple of things about each of the problems that you'll need to address. And then the last couple of pages are an opportunity for you to go through your notes and summarize. Got the theorems about segments and angles and circles. So, and then some problems that apply some of those theorems. So a lot of this will be on your own. Okay, so let's get started with our warm-up. Okay, on the axis below, we're going to do some graphing. New stuff, graphing our circle, and old stuff, graphing some lines. Let's start with the lines first. That might be a little bit easier. So we want to graph line y equals -5. So what I do is I find -5. 1, 2, 3, 4, 5. And y always has to equal 5. That means y is never going to go up here or down there. It stays at 5. This is how I know how to draw this line. There is no x in the equation, so really x could be anything. Then I go to x equals 5. 1, 2, 3, 4, 5. And again, x is not going to move over here or move over there because it is always exactly +5. So that's how I know how to draw this line. And then both of them intersect, which I can see that right here, and they're going to be tangent to the circle. So now I'm going to draw my circle. The two things I need to draw the graph of my circle would be the center, 0, 0. Radius squared is 25, so the radius is the square root of 25, or 5. So I find my center, and I go out 1, 2, 3, 4, 5, make a little arc, 1, 2, 3, 5, make a little arc, 1, 2, 3, 4, 5, make a little arc, 1, 2, 3, 4, 5, make my arc, and then I need to join those arcs with another larger arc, hitting a quarter of the circle at a time until I get the whole entire circle. And then I do see that what's true is that both of these lines are tangent to the circle. And then it asks me, the line y equals -5 is a horizontal line. It goes from left to right, and it is tangent to this circle at point 0, -5. And we're going to label this point of tangency point K. Right there. The line x equals 5 is not horizontal. It is the opposite of this, so I would call this a vertical line, and it is tangent to the circle at what point? It's tangent at point 5, 0. And we're going to label this point of tangency point P. Lines y equals -5 and x equals +5 intersect at one point. They intersect at 5, -5. We'll label this point M. And now we need to determine the length of segment KM. Well, it's a horizontal segment, so I can just count 1, 2, 3, 4, 5. And the length of segment MP, again, vertical, so I can count 1, 2, 3, 4, 5. Therefore, the length of KM is equal to the length of MP, and segment KM definitely then is congruent to segment MP. And what we just did is we used coordinate geometry, that's when we plot things on the coordinate plane, to prove the tangent segment theorem. The tangent segment theorem, if you remember, is if you have a circle and you have tangent segments that come from an external point, those tangent segments are congruent. Now we need to revisit how we calculate the distance between 2 points when those 2 points do not lie on either a horizontal or vertical line. So the picture that we're looking at here would be something like, here's x1, y1, and then we have up here x2, y2. So there's both a change in the x and a change in the y. So we need to use a more complicated formula. We can't just count horizontally or vertically. And that formula is based on Pythagorean theorem. A squared plus b squared equals c squared. C squared here is really our distance between the 2 points. So if we want d and not d squared, we have to take the square root, and it is the square root of the differences in the x's squared plus the differences in the y coordinates squared. A squared plus b squared equals c squared. And now I'll do one of these for you. We need to use the distance between the 2 given points. And if you notice, both the x coordinates and the y coordinates are unique. So we cannot use, it's not a horizontal or vertical distance, we have to use the formula. And the first thing I like to do is write this guy underneath the other point so that I keep the x's and y's lined up. And then I write my distance is the square root, and I'm just filling in, parentheses, 10 minus 4 squared, and parentheses, negative 5 minus 3 squared, (6 squared) and negative 8 squared. Remember, you must use parentheses. There'll be no negatives here because we're talking about distance. (36) and 64, which is 100, which is 10. All right, you can try that next one. All right, now moving on to problem 1. This looks a lot like what we just did, 2 lines and a circle, but it's couched in a scenario. The scenario here talks about 2 shot putters, the way they spin and the trajectory of their shot puts and where those 2 shot puts lie. And you just need to go ahead and follow along the guided example. It'll be very much like our warm-up problem. Problem number 2. Problem number 2 is some older stuff. Problem number 2 talks about a tangent being perpendicular to a radius at the point of tangency. So this is an old thing that we talked about. I think probably the most important aspect of this problem is that we've got 2 different units. So we either have to convert the miles to feet, which is what is set up here. As you can see, we're using our dimensional analysis to go from miles to feet. Or if you prefer, you could convert the feet to miles. Okay, we would just have that reversed. We'd have the 29,000 feet up here. We'd have the 5,200 feet in the denominator and the mile in the numerator. You could do it either way. And depending on what you choose here, your answer either is going to be in feet or miles. And here, if we just kind of maybe talk through this, that'll help us on that problem there. The diagram here, we have the height of the person, or how far off the Earth's surface they are, and we can see it's kind of going up to their eyeballs. We take that and the radius of the Earth, and that's going to really be the height of our vantage point. And the R is going to be the radius of the Earth, or, you know, if we're standing on some other planet, other circular surface. And D, if you see, is outside of the circle. So D does not represent the diameter. D is the length, or the distance, the person can see to the horizon. So when you're up high, you can see further to the horizon. Right, and then just kind of talking through problem 3 a little bit. Again, some old things, talking about sector area and how much of a play area this dog has. The first thing it asks you to do is to use 2 different color highlighters to highlight the 2 different sectors of circle that you see. We're going to use one color here for the small one. Okay, so the small one is the green one. And then maybe we'll use yellow for the larger one. So the 2 areas that we're going to be talking about and trying to calculate and then ultimately add together, the little bit of green and a lot more of yellow that this dog has. So we're going to find the 2 sector areas separately and then add them together. So I'm going to find the yellow area and add it to the green area. Okay. The doghouse is not part of the play space, only the stuff that's highlighted. And then we're going to go back and we're going to get our area of a sector formula. Maybe just to jog your memory. If you don't remember, then you have to get your notes. This is going to have to do with a fraction of the circle times the area of the circle. So hopefully that might jog your memory a little bit on what that formula is. If not, look it up in your notes or look it up online, and collaborate with a classmate to make sure you have the correct area. And then this last page here, this is a summary sheet for you, what we're looking for you to fill in the information, and then we actually gave you some numbers here so you could kind of work through the problem. Maybe I'll model the first one for you. This is the measure of an intercepted arc. So we're talking about this guy right here. I'm going to use a different color. Talking about the intercepted arc XY. It is exactly equal to the measure of its central angle. This is the one that's 1 to 1. The measure of a central angle is equal to the measure of its intercepted arc. So I could say the measure of angle XZY is 120, and the measure of arc XY is also 120. Angle XZY is a central angle. So this is kind of maybe the things that you want to write in this box. We're giving you the picture and some numbers. You're connecting to what fact must be true through the theorem, the vocabulary. So those are the kind of things that we want you to put on this paper here, and I think that will be helpful for tomorrow when we're reviewing and Thursday night to get ready for your test.